Okay, I invite. It's a good start, don't you think? More relaxed than this is not.
That's right.
That's,
This happened Monday morning, you panicked.
yes. So I invited Professor Vining to present his open problem, planning experiments when the response is a profile.
Let me finish making my mess.
No problem.
The intent on this is not for me to speak, but to get you all to talk about this issue. It's a true open research problem. This is not some data I've already collected. It's not an experimental situation, although I'm hoping we can talk about some real situations from our own experience. Is that fair enough? So we really are talking about the next level of industrial experimentation. This is becoming more and more important. Murad and I are working on actually, I've gotten permission from the U.S. Department of Defense to develop a large consortium. We have permission to communicate what we're doing with a group in Denmark and in Sweden. I'm working very closely with the Air Force Institute of Technology. NASA is very interested in this. I know China is getting ready to jump on this. It's just too obvious of an area, okay? So what do we do when our response is a profile? And let's just go ahead and make sure we understand what we're doing. I only have a few slides because I would like for this to be a real conversation. Thank you. We've seen a few profiles so far in this conference, okay? So Marcus was looking at profiles. In some sense, repeated measures designs often lead to profiles. Usually those profiles are over discrete times, and we're looking at it as discrete periods, okay? We're talking now about functional forms, and we really need to be able to estimate the functional forms. Okay, so it's a little bit different than the classical repeated measures, although that is not a bad starting point as a reference. So historically, it's either been a single number or vector representing a specific point in time. Again, with repeated measures, we might be looking at 4 or 5 time periods. Often the response could be a mapping down from something more complex, for example, an average. I'll give you a classic example of this. I've been wanting to work in this area for over 20 years. I was working in the early 90s with Alcoa. And I wanted to take response surface and apply it to something like a chemical reactor where we knew the observations were correlated over time. So far, so good? So, and that is an example of a profile. And in fact, it's a good example of it. But it didn't work for me because the law of large numbers for correlated data kicked in. I was trying to maximize the yield off the chemical reactor, okay? So again, this was at a relatively stable period. By the time I had enough information to estimate a good time series, the law of large correlated numbers kicked in, and I could replace it with just the average for what I wanted to do. So as a result, there was no gain for the complexity of the analysis. So far, so good? It was only when I started doing a little bit of work with the Air Force that I had the aha moment, okay? There, the issue is not being able to reduce everything to an average. I actually want to see how the profile changes and how I can control that profile. Notice that's a different question, okay? Now, in some sense, I'm controlling the profile when I control the average, but here in the military, they have a battlefield simulator, and they needed to be able to create the conditions. What if I change these conditions? How does that work? Very important. For NASA, what is going to control the pathway of a missile or a rocket? More importantly, what's going to control re-entry? Because, if you get outside of a certain range, you don't have a nice re-entry. Are we getting the picture on this? Okay, so that's the context. And again, this is a very important problem. And we have computing resources, we have insights. People have been working on functional data for some period of time. This is an opportunity, and again, this is not unique to me, to combine something from area A, experimental design, with area B, which would be functional data analysis. So far, so good? Okay? So, here's an example of some of the stuff that we would do. This is from DuPont. This is from a paper with Bill Woodall, J.D. Williams. It's from J.D. Williams' dissertation. It was published in the Journal of Quality Technology. What we're doing is looking at log dose and the percent of control. Notice this is not a straight line relationship. Beza had looked at, linear profiles, but it was just a simple straight line relationship, not a straight line relationship. Are we getting the picture here? Okay, much more complex. But this is the reality. This is what they need to control. Now, again, people have been working in profile monitoring for things more complex than straight lines. We can build on that work, but this is a context. The work they had to do here is, what do you mean by being in control? What do you mean by being out of control? So far, so good? But you see, the next step would be, okay, I'm out of control. How do I fix it? And that's where the experimental design technique comes in. Or even better, how can I establish a feed-forward or a feedback control loop? Okay, so once again, I know I've got a problem, but then how can I react to correct it quickly? This is building a lot off of what Murat was talking about yesterday. In order to do that, you've got to have some understanding of the system, and the quickest way to get an understanding of the system is a designed experiment. Are we getting the picture? Okay? Here is an example from the Air Force. This was published in Quality and Reliability Engineering International. Murat, do you remember it was what, 4 or 5 years ago?
11 or 12.
Yeah, so it was probably 3 years. It's probably 12.
Yeah, 12.
This was an Air Force officer named Storm's master's thesis at the Air Force Institute of Technology. It's a very crude attempt to be doing experimental designs for profile data. Again, this is highly sanitized. This was published. Okay, I can't deal with any kind of really hard military data. Okay, even I can't get to it, and I like that. Trust me. I traveled too much to places where I would get in real trouble. Okay, but what they're really looking at is, if I remember right, this is an example to illustrate what they were doing. The goal is to see how the surface here changes over time in terms of experimental conditions. Yeah, this will actually could actually go to the point of the profile could be spatio-temporal, but certainly temporal is part of the idea of the profile. But it could also, again, just be temporal. Okay, so that I think are the background I wanted to do. It's up to everybody here now. I mean, I'd love for us to have a conversation to ground ourselves. From what I have described, or do people have examples of things that might fit into this situation? In terms of the publications that will come out of this, this is a real problem. Okay, I think we've got to. This is a real problem. This is not something where you would be generating a solution in search of a real problem. So having a real problem context should be guiding our research. But at the same time, I think we will be developing things that will apply to a broad class of problems. For example, things that we would be doing for the U.S. military would apply to our PhD student in food technology. Similar kind of issues. All we just got to do is understand what that profile is. I hope I'm making sense. So with that, I'm opening it up for conversation. This is not my job. It's your job now. What kind of situations do you see where you might want to plan an experiment where the response looks like something like that? Or I think this is a little easier for us to absorb. But again, I'm looking for it even to the point of images and how the images change. Is this okay? This is either going to be a rich conversation or a very short one.
Yes.
Okay? Yeah, Carla. Here. I don't need the mic anymore.
We are working with like climate data, and I see a similar pattern. For example, have a simulation model and like observer data, and we want to see which parameters can we change in our simulation model that can predict the data, like temperature over time. So have like daily hurricane paths, thunderstorm paths, and we have these profiles. And it's not an answer. It's also a problem that we're facing that's similar to that one.
Yeah, and a lot of simulation experiments are going to involve this so that you can build a simulator that will then mimic what's going on with that simulation. Okay? Any others?
I was also hoping that Afrania will come. No, because you asked when I was talking about the functional
Yes.
I think
data.
it's better
The topic that we're discussing is that in the experimental design, sorry, when you do the experiments, if your responses are functions, I mean, it's interesting because that we're now talking about as an open problem, but it's an old one as well. I mean, a useful method for model building, one, there are two parts, by Box and Hunter in Technometrics paper, like 56, 57, I want to say.
59.
Okay.
It couldn't be before 59.
No, okay. Yeah, you're then 61 maybe. So, but it's an earlier issue of Technometrics where they had basically for different settings of a chemical reaction profiles of the chemical, like a concentration profiles. Let's say it starts from nothing and then it goes up and reaches an asymptote. Their approach was very simple. Since we're going to have these, we know this is a chemical reaction. We're gonna have these profiles of concentrations. What we do, we just look at the rate. I mean, chemical reactions have a rate. So summarize the whole profile in terms of a rate constant, basically, and then make that a response, for example. So that was a really, really nice paper. It's a very nice way of looking at it. So that has been, like, when people ask me about functional responses, and I would say, yeah, that's what you do. You just try to model the profiles that you have or the responses that you have. Any kind of model for that matter. It could be a time series model if you want it that way. And then make your parameters, the parameters of that model, your response. And you can have just a single parameter as in the reaction rate, or you can have multiple parameters. And it becomes a multi-response problem again. Or as Jeff said, people used to do just take a look at the average. Of course, when you do these summaries, like averaging, you lose information. There might be more information there. So can we take advantage of that? And then, as you said, functional data analysis, the Ramsey and Silverman work can help here. But I think another thing that you mentioned, Jeff, this is very, very interesting because this is a POLI-USP conference, because this could be a kind of a nice somewhere in between. Because if it's an SPC situation, or if you're monitoring profiles, even if everything is in control, it doesn't have to be out of control. If you see too much variation, you might want to know what's affecting that you see so much differences, and process seems to be in control, just that have naturally high variation. But if there is an out of control situation, definitely you want to investigate. There we go into, okay, we're going to experiment, we're going to set certain x's in certain ways and then see the profiles, how they vary, and find the important x's and maybe have an optimization. So that's another interesting. If you have response profiles, how do you do optimization? How do you response surface methodology? Here's another open problem for all of us to work on, as far as I know. If you have multivariate, multiple profiles to deal with, how do you deal with that? It's another open problem.
And that's a very real problem because like Eric
yeah.
The blast furnace.
Yeah.
Yeah.
One of my colleagues up in Luleå is working on that, and he had a nice paper last year in quality engineering that he published with another colleague. But what I'm trying to say here is it's an open problem, but there are already other areas who worked on that worked on similar, like functional data analysis, one area. Another one, if you want to get into this issue, is system identification. In chemical engineering, there's a system identification group. What they do, they have time series X's and time series Y's, and they try to find that transfer function, right? One of the projects that we're working on in Luleå is kind of, what is the connection? Can we use the system identification tools and do it in the way that we understand it, design of experiments, for example? Because there is a mismatch. In the system identification, what they say is this. Here are like two X's affecting Y. Let's find a transfer function. Right? That's what they do in system identification. In design of experiments, we often say, here are a bunch of X's. We don't know whether they are important or not. Let's investigate that first. Once we investigate that, let's figure out how they are affecting the response. And that leads to, for example, in time series analysis, transfer function noise models, right? So there are many similarities between these several disciplines and what we're trying to achieve here. So if you can, I mean, I know we're having it for just industrial statisticians, but that could be a really nice opportunity to collaborate with other researchers in your universities and kind of join forces. Again, from stat department, functional data analysis person will be a wonderful person to team up with. If you have a chemical engineering department, you can team up with people from there and says, okay, is there a system identification guy here? Okay, here's the problem that I have. What do you think? And then just, have some joint research that way. So in that sense, it doesn't have to be just, oh, it should stay within this room. It can involve other disciplines and other people from the other departments.
Just a quick comment. I see similarities. What Afrânio has presented yesterday, it could be applied here because he was modeling at the same time or simultaneously the mean and the variance. And why not, instead of using your type of response, use a profile function?
Yeah, but if I understand, for each observational unity, you've got a profile. That's it. Yeah.
Each experiment yields a profile rather than a single outcome.
Okay.
A functional form.
Is a functional? I don't know if it's ready, but it's functional. But the form of this profile, probably there is a reason for this curvature. When I saw this figure, I connected with things that I have been taught about those response models. I think there some nonlinear models can be applied this, but it has to be connected with functional data analysis. I'm not sure if it's ready for use. I'm not sure.
I think in this meeting I start to realize that the thing we are lacking from design of experiments viewpoint is the idea and the spreading the idea. The idea is already there. There are papers and theses of sequential design. We don't teach sequential design properly, and we don't automate our process to do sequential design. So when we do something like, well, there is a problem, practical problem in Brazil now. This is the huge tests they are done with item response theory analysis. So this become popular now, and item response theory becomes now a popular theory, a popular way to analyze data and go to the press, and statisticians are coming to talk about that. But even then, we don't have like ordinary testing systems that do adaptive design to get a better test. So I think we are like maybe 30 years behind on this subject only. And then I don't know in the other fields of industry or whatever, but we don't do this in some very simple process we could do. Something like, it don't need to be instantaneous. I can take one day to analyze the data and propose another point, something like that. We don't do this. We should. And then I think it's, in many fields we will find something like that. Now, we don't do the nonlinear version, and we don't get the, where are the, you know, most important variances coming from, where we should put our replications to minimize this variance. We don't really do that.
I have projects where when I talk to people sometimes, they describe the problem and they will tell me the response is as a singular value. I mean, sometimes it's a single value. And then if you dig deeper, then you realize it's a profile that they're getting, and they only report the asymptote, the final value, or they average it out and then they tell you that. So not always, of course, not in all experiments, but in few cases when okay, what is the response? Here's the response. So how did you get it? Oh, it is when the reaction happened, something happened, and it reached after 10 minutes. That's the value that we look at. But aren't you interested in what's happening until that point? Yeah, it would be nice, but we thought it's not possible. So that's so that is. I mean, you're faced with these things. So I think it is more frequent than we would like to believe or we think. So it's a challenge.
We've been trained for so long to think in terms of the single number or a small vector that we don't think in terms of a bigger picture. And that's the reason why I said this is an open research question, that we don't have solutions to this. You know, that's what we're trying to do here, is to throw this out to you, understanding this is going to be a hot area, and it's wide open at this point. But I hope we appreciate that there is a real opportunity. Now, in some cases, mapping it down to a single number is not a bad idea. It's simple to understand, but there are other problems where you really do need to understand how that profile changes. Like temperature profile of a chemical reaction. You know, that really could be that it's that profile that controls the quality. Deviations from that profile are going to lead to problems. And being able to react to how that deviation is and to bring it back leads, as I said, to the notion of a feed-forward or a feedback control loop. So again, I keep wanting to emphasize, we don't have any solutions here. Here's an opportunity for you all to help begin to generate solutions.
One last thing I would like to say. From my experience, when I talk to hardcore statisticians, no offense, Jeff, but they are so worried about the analysis, so concerned, and how can we make generalized super mixed, they go crazy about how the design aspect is not a concern for a lot of statisticians. I'm really shocked. I mean, the only time that I think they are worried about maybe is in the power calculation, the sample size. Otherwise, they are not worried about the designing the experiments. They're worried about the analysis. So I think here we should keep in mind that there are both. So if I know, we talked about it with Andre as well, if I know that the response is going to be some kind of nonlinear, because I have an idea, based on some first principles of the system, of the process, I know the behavior of the response will be something like that. Of course, I'm going to get different results for different experiments. So should I do a factorial design or a fractional factor or optimal design? What is the differences? What am I gaining by doing this as opposed to that? Designing experiments for the response, type of response that we expect could be a challenge, and it will be, of course, case specific, but it will be a challenge. So we shouldn't just worry about the analysis aspect of these things, but also how would we effectively design experiments for this type of responses.
I think that in a first moment the concerns about the analysis, that's the way I see, is because when I see a profile with this form, I guess the intensity, the velocity that this curve grows up, or the value that is the asymptote the curve gets. I think there is much engineering information there for the process. So I guess the modeling is important to get information. But when I see a nonlinear behavior like this, when I think about the design, I'm automatically connecting which kind of model I will use to analyze this data. So first came the model I will use to analyze, and after what is the best design to estimate that model. So when you say, oh, it's a factorial design, is a good design for this experiment. Well, depends the model you will use. Is a linear model or a non-linear model? If it's a non-linear model, maybe when I have a well-specified model, I can start to think about the information metrics, and Julio expert on this subject to find the best designer.
Exactly my point. So, but if the model that I have in mind is a linear additive model, I go factorial designs, and the two-level designs I start with, and the first order approximation would be fine, maybe, I hope, and I can check for the curvature. But if you have profiles like this,
okay.
I'm saying that we should be worried about what kind of set of experiments we're gonna use. Should we stick with the factorial? Should we stick with the two-level fractional factors, for example, or should we come up with a completely different set of experiments because we know the profile the response would be maybe nonlinear, for example? What is the best design for that type of response is what I'm saying. So not just the considered analysis aspect of the problem, but also how would we design the experiments? Maybe I wasn't clear. I'm exactly saying what you're saying. Factorial designs may not work out for one particular type of response that we expect to see. So there are two. I mean, I'm just trying to say that there are several avenues we can just kind of start doing research in this area, and they are open problems as far as I'm concerned. And I might have a limited view, of course.
Actually, the question here is a nonlinear behavior, but I guess the general question is, my response is a function. How to design experiments for that? Well, the things I saw about it is still on very early stages. I saw our fresh result is about ANOVA for simple treatments or things like this. I guess some regression models for this exist, but all linear, very limited.
The problem is that I was at least 10 or 15 minutes late. And then if this...
You want to see the previous slide?
Yes, I would like to.
It's not real complex.
No, but just to...
1,
Oh.
2, 3.
So you're not too late.
Okay, but I might assume this should be something you are trying to investigate. Yeah. But a dose response problem, if this was a setup, I have this data and I need to plan another experiment, I have some clues. I think this should be...
How would you analyze it, for example? You would fit a model to all of these and use the parameters of the model as response?
Something like a beta or logistic model or whatever, or probability analysis or whatever, depending on the field. You know, people from pest control, they will prefer go to probability analysis, and then
For those response, there are models, right?
yeah. So then I will look at it's very likely that you are most interested in parameters that are related to the both asymptotes and the everything.
Yeah. The background on this is these are real data from DuPont on a herbicide. And
Okay.
And this was for profile monitoring for control charts. So it was a JQT paper from about 2007. It was work out of Virginia Tech, but it was Bill Woodall's group that was doing this. So there they were dealing with more complex profiles than just a simple linear regression function. I think they've even done work that involved nonparametric regression, because you get this one, as you said, this a logistic or a probit is probably a good starting point.
Yeah.
But of course, they're dealing with the issue of what do you mean by being in control? What do you mean to be out of control? How do you define when something is different? You know, those are fundamental issues that we have to consider here, because it's only when it's different that we want to change it. Am I making sense? It's a whole new world, isn't it?
Yes.
It's an exciting new world. So let me get it back on.
The way I understood, even in a very simple factorial, two-level factorial approach, we may have for each treatment a profile like this. And for a specific combination, the profile could have a completely different function, could be linear. Yes, so we start to understand what is making the profile to change its shape, even in a very simple two-level factorial approach. I still don't have a clue of the mechanics of the model.
Oh.
I'm starting to realize what is impacting the response.
I just want to give you another example, and again, this is from the Air Force, and it's fairly important to them. Now, again, I've seen sanitized data, but I could share the sanitized data. That's another paper that's coming up, but it's looking at shrapnel, pieces of metal, going through the skin of an aircraft, and that will create a flare, flame. Flame, aircraft, is that a good combination or a bad combination? Okay, so the Air Force really needs to be able to model that flame, that flare. So notice it's going to have, at some point it starts, it expands, and then it's going to go out. But I hope you appreciate that from the Air Force perspective, it's crucial to be able to model that, especially if it occurred anywhere near a fuel line. I mean, these are the kind of problems that we're dealing with, very real. I hope we can all begin to see in our own work, where this could be very, very profitable. Again, I'm not suggesting this is the answer to all problems, because we've been very successful with getting it down to a single number. So I don't want everybody to create a new hammer and everybody's going to go for their new nail. But this is, I think, a wonderful area for us to explore.
Maybe those profiles were in the previous slide were misleading because they all look quite similar. So you just said, okay, just fit a, whatever model. But how about this? Now, let me make it up, because then you say, well, it's a trivial problem to deal with. How about I'll make it a bit more interesting. For certain experiments, you have a certain shape. For other ones, some discontinuities in the response surface. You have completely different shapes. The model that you had in mind can fit to certain experiments, but cannot possibly fit to others. Now, what do you do then? How do you analyze the whole thing? And there can be changes, drastic changes, some discontinuities in the response surface as well. So how do you deal with that problem? How do you still identify, even in that situation? That's the reason I gave in the early paper that I mentioned, Box Hunter paper, a useful method for model building. They have always the same shape. So they could summarize all shapes with just the constant, reaction constant, the rate of change. That's what they could do. They could so you don't need the profile at all, because one number summarizes the whole thing. So you see which x's are affecting that rate, and then you analyze your data accordingly. Now, what if your model, it fits very well to some experiments, responses from some experiments, but not to all? So what do you do then? That's, to me, it's another open area to get into.
I'll show you one more example, and I think we can all relate to it. I'm from the southern part of the United States. And we really barbecue. And when we barbecue, you know, it's hours, very low and slow, okay? And I'll show you a rough sketch of a very important profile if you're barbecuing, okay? So. And we do pork all the time, okay? In Texas, it would be beef. So poor Marat, you know, he can't eat my pulled pork, okay? So this would be our internal temperature of the meat is about the goal usually is about 205 degrees Fahrenheit. What is that? About 96, 97 Celsius. Okay. Does that give you kind of a ballpark on this? Much higher than you would ever normally do. But we're dealing with very fatty pieces of meat with bone. There's connective tissue. There's several transition points. And those transition points are extremely important because that's when making sense. Am I making sense? Trying to model this as a simple linear regression function misses the most important pieces of information. This is an example of a profile which I can control with heating rate and the temperature that I'm shooting in the smoker around it. Are we relating to what's going on with this? But again, it's a real problem to ignore this because when I'm sitting there, and again, this takes 8 or 9 hours, it's nice for me to be aware that there's not a problem because the internal meat temperature isn't changing, that there's a chemical reaction going on within there, and it's an important chemical reaction. So here's something as simple as food technology is related to weapon systems, which would be related to financial systems, which would be related to climate issues. That's the reason why I said this is a great area. Does this help clarify for people exactly why we got to be careful with some of the things that we do? This is not true non-parametric. I don't even know how I would want to model that. You want to know the truth. The first thing I'm going to try to do is capture what's going on there. Is this cool? Okay.
Suppose you don't have a model and then you capture a lot of information. You already have a lot of, you gave us a lot of information. Then you know where you suppose the more, you know, the more critical bits, the more, and the ones that you are suspecting has more variance or in some sense less control. So I think it will be desirable to build a model, a tentative model to get this piece. For instance, for this I will do something like, I'll do, he draws something like very straight lines, and then I will do like segments and threshold points for the segments. And then it is a nonlinear model, of course, but condition on segments is linear, so we are trying to estimate the thresholds, the time points. So you.
But this is going to depend upon the external temperature to the meat and the heat rate. So those transition points will change depending upon that.
Yeah.
Oh, it's a fascinating problem. And I haven't started to collect the data on this yet.
Okay.
One approach would be, for example, like interval or even like a Ramsey-Silverman functional data analysis approach would be, for one experiment, you have a profile like this. Then what you do for every time, it's discrete there. I mean, it looks continuous, but it's discrete, of course, because you sample discretely. You cannot sample continuously. So at each time point becomes response, meaning at times equal to 1, for all experiments, I have a response. At times equal to 2, I have a response. So now you turn the problem into multi-response and then analyze it that way, for example. Yeah. Okay. So it's something similar to what you're saying, intervals, but you can do it literally for every time that you collect data, because for each experiment you have a value from the profile.
It's like become a longitudinal data.
It's longitudinal, but in some cases we're dealing on a continuous scale. So we've got to decide what's the sampling frequency. And if we oversample, then we're reacting to noise. If we undersample, we're missing important features. Notice this is not a trivial problem.
But try to draw another piece of meat. Depending on maybe the size, you have a parallel or drawn to the right or whatever, isn't it?
Yeah, different piece of meat, different size, for example.
Uh-huh.
Is it a different color?
No, same color.
I'm colorblind.
Oh,
Can you see that?
yes.
I can't, but that's okay. Okay. So, is that different? Is it the
Okay, now I get the picture.
yeah. This.
But it could be shifted to the right somehow. Or
Amen. Yes.
but
And-
you can imagine that the temperature that the reactions, that important reactions occurs, might be quite similar, isn't it?
We would hope so. But I mean, coming back to it, one way to look at this is these are functions of, call it the temperature that we're trying to keep the smoker at, size of the meat, okay, type of wood.
Okay.
For example, in where I live in Virginia, again, we can all relate to food, right? Yeah. I have a lot of oak trees in my yard, so I would use oak, but the people who really do the top level barbecue would use something like apple wood or cherry wood, a fruit wood, which imparts a different flavor, but will have a different characteristic there. So the experiment is how do those things influence the temperature profile, and what does that temperature profile tell me about the quality of the product? Okay, so I know the profile, ultimately the quality is a function of the profile. Which is the mechanism here, but it's not a simple mechanism that I could control. You know, I can make changes here. I mean, that's my thought process on this at this point. But again, remember, this is not a solved problem. It's whatever people want to do with it. My goal was to get you excited about it. Yeah. Free samples anytime. You got to come to Blacksburg, Virginia. Bring a lot of beer. Okay.
Understand this in experimentation, it can go really horribly wrong as well.
Trying to fight with the guns I've got, to sample or to take a grade enough for not loss information, and try to analyze as a longitudinal data. It's reasonable.
I don't know what's going to be. Yes, it is reasonable. No question about that.
Because I can take the information about how this process to check if they are similar or not. I can do this using longitudinal data models. The question is, you've got lots of data, and each grid I can take a grid smaller probably, and it double the file. The autocorrelation becomes high for these situations. The computation is not optimized to analyze profiles, so the computation will be hard. But I think it's possible. But it's just a completely ignorance about the functional data analysis. I think. I guess for simple situations where you can fit polynomials or linear models, there are something already implemented, and you can check if different between groups, things like this. But I don't.
The beauty of this is there's no single right answer.
Yeah.
You know, there are lots of approaches to this. They're bad answers.
Yeah.
Okay. You know, but frankly, there are going to be multiple approaches to this.
Yeah.
That's why it's going to be an incredibly rich area.
Yeah.
Yeah, and it's going to be, in some cases, very situation specific. Those are solutions I do not like. One of my problems with technometrics recently has been it's been very much so situation specific, it does not generalize. I see the opportunity to develop solutions here that do generalize, but you have to understand the specifics of your particular problem to do that. Okay? So again, with what I might do with this, because I'm just biasing you, and I haven't even really thought about this. But I know this is something that is of interest and would be fun for me to do. It would take me a year to do it because I only barbecue, you know, a few times a year. Even if I did a 2-cubed experiment and replicate it, well, you know, it's a long time. And my wife doesn't let me drink beer all day on Saturday to do this. I have to do it when she's away. My wife doesn't let me drink beer all day on Saturday to do this. I have to do it when she's away.
I think, just one comment. I think we are trained in our course, in statistics course, for me also. I think it's more trained to data analyze, to make analysis of the data than how plan an experiment. Because I think for me also, we have just to, I think no more than one class about how to design our experiments. And then you start to begin 1 factor, 2 factor, and how to analyze, make ANOVA and something else. So, well, I don't know how to correct this when we are teaching DOE. Most of the classes are concentrated not to plan experiment, to think how different ways to plan experiment, but how to analyze. So I don't know how to change this. Something else? More questions, comments?
We got almost an hour.
Almost.
Yeah.
Yeah, it's okay?
I'm fine.
Okay. Oh, thank you.